Hello viewers, I am Asghar Pasha, Assistant Professor, Department of Mathematics, MS Rama Institute of Technology. I will be doing problems on Cauchys differential equation, which is a continuation of my last session. Problem number 5 on Cauchys differential equation. Solve x to the power of 4 into d cube y by dx cube plus 2x cube into d square y by dx square minus x square into dy by dx plus xy equals to 1. You can see the coefficient of d cube y by dx cube is x to the power of 4. It's not x cube. We want this to be x cube. We want coefficient of d square y by dx square to be x square and dy by dx to be x. So it can be converted to Cauchys differential equation if we divide throughout by x. So when we divide throughout by x, we get a Cauchys differential equation. Coefficient of y is constant and then RHS is 1 by x. This can be converted to linear differential equation with constant coefficients using the substitution x equals to e to the power of t, so that t becomes log x and all the terms with variable coefficients get converted into terms with constant coefficients, d into d minus 1 into y, d into d minus 1 into d minus 2 into y and so on, where d represents derivative with respect to new independent variable t. If I substitute all these things in the given differential equation, we obtain d into d minus 1 into d minus 2 into y plus 2 into d minus 1 into y minus dy plus y equals to 1 by x. This part is x. X is e to the power of t. Multiply and simplify the equation to get this form. D cube minus d square minus d plus 1 of y equals to e to the power of minus t. This is a differential equation with constant coefficients. As usual, solution of this consists of two parts. One is CF and another is PI. To find CF, consider auxiliary equation, which is obtained by equating the homogeneous part of the equation to 0. So this is auxiliary equation, m cube minus m square minus m plus 1 equals to 0. You factorize it to get the roots minus 1, 1 and plus 1. So I have one real root and one real root minus 1 and two real repeated root 1 and 1. Complementary function corresponding to the root minus 1 is c1 into e to the power of minus t. Here t represents new variable because we have converted x to t using the substitution x equals to e to the power of t. So this part is corresponding to the root m equals to minus 1. And this part c2 plus c3 t into e to the power of t corresponds to real repeated root 1 comma 1. Now we have to convert this in terms of variable x. We can use law of indices here. We can write e to the power of minus t as e to the power of t whole to the power of minus 1, and then t is log x, e to the power of t is x straight away. So it gets converted to the form c1 by x plus c2 plus c3 log x into x. This is complementary function. Now particular integral. It's 1 over f of d into e to the power of minus t. RHS is 1 by x, which is 1 by e to the power of t, nothing but e to the power of minus t. This is type 1, e to the power of minus t. According to type 1, we have to replace a by d by a. A is a coefficient of t here, which is minus 1. If we replace d by minus 1, then denominator becomes 0. D cube minus d square minus d plus 1 becomes 0. And hence the rule is you have to multiply the independent variable and differentiate the denominator. It's t into 1 by derivative of f of d is 3d square minus 2d minus 1 operated on e to the power of minus t. Now you can apply rule 1, that is replace d by minus 1. You can see we have replaced d by minus 1 here, 3 into minus 1 whole square minus 2 into minus 1 operated on e to the power of minus t gives final solution as t into e to the power of minus t divided by 4. Now next step, convert it in terms of x. T is log x, e to the power of minus log x. You can use law of indices as well, or else fine, e to the power of log of f of x concept you can use. E to the power of log of f of x is f of x. So we'll get pi as log x divided by 4 to the power of x. This is pi, which is a solution of the whole equation containing no arbitrary constant, but it is not the general solution, because general solution of a second order ODE must contain two arbitrary constants. Those constants are present in complementary function. So the complete solution of the given differential equation is Cf plus Pi, which is C1 by x plus C2 plus C3 log x into x plus log x divided by 4x. Now problem number 6. Solve x square into d square y by dx square minus 2x into dy by dx minus 4y equals to x square plus 2 log x. Okay, RHS contains terms independent of y, and LHS is, of course, this is a Cauchys differential equation. It can be reduced to differential equation with constant coefficients using the substitution x equals to e to the power of t. So the t is log x and x dy by dx is d1y, x square d square y by dx square is d1 into d1 minus y, where d is dy by dt. Substitute all these things in the given differential equation. LHS is, of course, as usual. Now RHS, x square, x is e to the power of t, so x square is e to the power of 2t plus 2 into, in place of log x we have a t here, 2 into t. Now simplify this, simplify the LHS, we get d square minus d minus 2d minus 4 operated on y equals to e to the power of 2t plus 2t. So the resultant is a linear differential equation with constant coefficients. Now write auxiliary equation, which is obtained by equating the homogeneous part to 0 after replacing d by m. Even you can write d also there. So solution of the auxiliary equation is m equals to minus 4, m equals to minus 1 and plus 4. Now the part of Cf corresponding to m equals to minus 1 is C1 into e to the power of minus t, and for m equals to 4, C2 into e to the power of 4t. Convert this in terms of x. We can write e to the power of minus t as e to the power of t whole to the power of minus 1, and e to the power of 4t as e to the power of t whole to the power of 4. Next, convert, write e to the power of t as x, so it is c1 into x power of minus 1 plus c2 into x to the power of 4. So complementary function of the given differential equation is c1 by x plus c2 x to the power of 4. Now consider pi. Pi equals to 1 by d square minus 3d minus 4 operated on e to the power of 2t plus 2t. You separately operate on two terms, because first term is e to the power of ax type and second term is a polynomial. So it is 1 by d square minus 3d minus 4 operated on e to the power of 2t plus 2 times 1 by d square minus 3d minus 4 operated on t. I will call the first term as pi1 plus 2 times second term as pi2. Consider pi1, which is 1 by d square minus 3d minus 4 e to the power of 2t. So coefficient of t is 2, which is a. According to rule, we have to replace d by 2. So just replace d by 2 here, and you will get the value of pi1, which is e to the power of 2t by minus 6. Now pi2, it's 1 by d square minus 3d minus 4 operated on t, that is equals to, now it's a polynomial, you have two techniques, one is division method and the second one binomial expansion. You should be careful when you are using binomial expansion. Denominator should not contain d. So I need out of two terms, so one term as 1, so I have many options here. I can take d square common, minus 3d common, as well as minus 4 common. So the best one is minus 4, otherwise I cannot ignore the terms in the infinite series. So take minus 4 outside. then this becomes 1 divided by, when you take minus 4 outside, 1 by minus 4, 1 minus d square minus 3d divided by 4 operated on t. Take this to numerator, it is minus 1 by 4, 1 minus d square minus 3d divided by 4 whole to the power of minus 1 operated on t. Now expand it, this is 1 minus x whole to the power of minus 1 expansion, which is equals to 1 plus x square plus x cube and so on. So 1 plus x, this part is plus x, 1 plus x d square minus 3d plus by 4 plus x square term. I have not written x square term because this is a polynomial of degree 1. So second and higher order derivatives of t are 0. So I have not written it. And in the next step, even I have ignored this d square by 4 term, because d square by 4 operated on t is 0. So we have minus 1 by 4, 1 minus 3d by 4 operated on t. Now you multiply t here, 1 into t is t minus 3 by 4, derivative of t is 1, so it is minus 1 by 4 t minus 3 by 4. This is pi2. Substitute in the pi expansion, in the pi expression. Pi is pi1 plus 2 pi2, so it is e to the power of minus 2t by 6 pi1 plus 2 times pi2, which is minus 1 by 4 t minus 3 by 4. Now write e to the power of 2t as e to the power of t the whole square minus half into, after simplification you will get it as t minus 3 by 4, half into t minus 3 by 4. Replace e to the power of t by x and t by log x to get the pi as minus x square by 6 minus half into log x minus 3 by 4. Therefore, the complete solution of the given differential equation is c1 by x plus c2 x to the power of 4 minus x cube by 6 minus half of log x minus 3 by 4. Now problem number 7. Solve x square into d square y by dx square minus x into dy by dx plus y equals to log x. This is a Cauchys differential equation. This can be converted to a differential equation with constant coefficients using the substitution x equals to e to the power of t as usual. So the resultant equation is d into d minus 1 into y minus dy plus y equals to t. Now simplify this, it becomes d square minus 2d plus 1 of y equals to t. So auxiliary equation is m minus 1 the whole square equals to 0. Solve this equation, you will get roots as 1 comma 1, which are real and repeated, and hence complementary function is c1 plus c2 into t, independent variable, into e to the power of t. You convert that in terms of x, we get cf as c1 plus c2 log x into x. Now pi part. Pi is 1 over f of d into phi of t. Phi of t is t, f of d is d minus 1 whole square. Now d minus 1 whole square can be written as 1 minus d whole square as indicated. Take that to numerator, it is 1 minus d whole to the power of minus 2 into t. You expand it using binomial expansion, because it is 1 minus d whole to the power of minus 2, 1 minus d whole to the power of minus 2, the standard expansion, according to 1 plus x whole to the power of n, which is 1 plus nx plus n into n minus 1 by 2 into x square plus so on. If you expand it, you get this 1 plus 2d plus 3d square plus 4d cube and so on. Okay, so the same thing here. Operator on t, ignore derivatives of order greater than 2, because it's a polynomial of degree 1, we get t plus 2 as answer here. So pi is log x plus 2. Therefore required solution is y equals to c1 plus c2 log x into x plus log x plus 2. If you want, you can find pi in this case using division method also. You can see we have 1 divided by 1 minus d the whole square into t. Of course, in this case binomial expansion is easy. I'll teach you what the difficulty in division method, because I have to expand it. If I expand 1 minus d whole square, I'll get 3 terms, maybe lengthy in this case. But in most of the cases, division method is easy. Here, as there are only 2 terms, expansion is easy, and we got pi in 2 steps only, standard expansion. Now 1 minus d whole to the power of minus 2. What is division method? Your pi is 1 divided by d minus 1 whole square operated on t. You expand it, d minus 1 whole square is d square plus 2d minus 2d minus 2d plus 1. I'll write this in increasing order. 1 minus 2d plus d square operated on t. Okay, the first term is t, t by 1 is t, 1 into t is t, this one, 1 into t is t. Next, this part, 2 times derivative of t, derivative of t is 1, minus 2 into derivative of t is minus 2t, so you will get minus 2t here. You subtract this, you will get 0 and plus 2t here. Next step, 2t, this 2t divided by 1 is 2t, t plus, sorry, this is not 2t, it is only 2, because derivative of t is 1, this part, derivative of t is 1, so it is only 2, minus 2 into derivative of t. So it is, there is no t here, this is only 2. So 2 by 1 is 2, so I will get 2 here, this is 0. So this t plus 2 is my pi, which is same as this one. Let me repeat, 1 minus 2d plus d square. I have written this in increasing order. T is the dividend. When you do it by division method, you will get 0 as remainder and t plus 2 as quotient. So t plus 2 is the particular integral. Now, solution is y equals to cf plus pi. Next question, problem number 8. X square into d square y by dx square minus x into dy by dx minus 3y equals to x square into log x. This is Cauchys differential equation. This equation can be converted into differential equation with constant coefficients using the substitution x equals to e to the power of t, so that t becomes log x. And the other terms with variable coefficients gets converted to dy, d into d minus 1 into y and so on, where d represents derivative with respect to new variable t. Substitute all these things in the given differential equation, we get d into d minus 1 into y minus dy minus 3y equals to RHS x square. X is e to the power of t, so x square is e to the power of t the whole square, nothing but e to the power of 2t into log x. Log x is t here. Next, d square minus d minus 3 of y equals to e to the power of 2t into t. Simplify this to get d square minus 2d minus 3 operated on y equals to e to the power of 2t into t. Okay, this is a linear differential equation with constant coefficients. Its auxiliary equation is m square minus 2m minus 3 equals to 0. You factorize it to get the roots of the equation as m equals to 3 and minus 1. Complementary function corresponding to the root 3 is c1 into e to the power of 3t, and corresponding to minus 1 is c2 into e to the power of minus t. Write e to the power of 3t as e to the power of t the whole cube, and e to the power of minus t as e to the power of t minus 1 the whole cube. So CF is C1 into x cube plus C2 into x to the power of minus 1, which is C2 by x. This is CF. Now PI, it's 1 by f of d, which is d square minus 2d minus 3 operated on e to the power of 2t into t. Yes, this is like e to the power of ax into some function of x. This is type 4. According to the rule, we have to take out e to the power of ax outside the operator after replacing d by d plus a. Identify a is 2 here. So replace d by d plus 2 whole square minus 2 times d plus 2 minus 3. So this is outside the operator now. This operator operates only on t. So type 4 got converted into type 3. This is a polynomial. So two methods as I mentioned earlier. Okay, now you simplify this to get e to the power of t into 1 by d square plus 2d minus 3 operated on t. Here we have used a binomial expansion. 1 divided by minus 3, I have taken minus 3 outside, so it is 1 minus d square plus 2d by 3 whole to the operated on t. Take this to numerator. To get this 1 minus d square plus 2d by 3 whole to the power of minus 1 operated on t, you expand this, which is 1 plus x square plus x cube and so on. After ignoring the terms, we get 1 plus 2d by 3 operated on t. Now you multiply, of course in the second case you operate it. Minus e to the power of 2t by 3, when you multiply it is 2 plus derivative of t is 1, so only 2 by 3 remains. Next you convert it in terms of t. You can write e to the power of 2t as e to the power of t the whole square. T is log x plus 2 by 3, e to the power of t is x. So I get pi as minus x square by 3 into log x plus 2 by 3. The complete solution is y equals to CF plus pi. Problem number 9. Solve x into y triple dash plus y double dash equals to 1 by x. This is not Cauchys differential equation. It's not in that form, but can be converted to Cauchys differential equation. We want coefficient of y triple dash to be x cube and coefficient of y double dash to be x square. So it's easy. If I multiply throughout by x square, I get x cube into y triple dash plus x square into y double dash equals to x, which is Cauchys homogeneous linear equation. Now as usual, make the substitution x equals to e to the power of t to reduce this to an equation with constant coefficients. After substituting all these things in the given differential equation, we get d into d minus 1 into d minus 2 into y plus d into d minus 1 of y plus 2y equals to e to the power of t. Multiply, it's d cube minus 3d square plus 2d plus d square minus d of y equals to e to the power of t. It reduces to this form, d cube minus 2d square plus d of y equals to e to the power of t. This is linear differential equation with constant coefficients where d represents derivative with respect to new variable t. You solve this equation, take m common, m into m square minus 2m plus 1 equals to 0, which implies m into m minus 1 equal to 0. So m equals to 0, 1, 1. So I have one real root and two real repeated root. 1, 1 are real repeated. Corresponding to the root m equals to 0, we have part of CF as C1 into e to the power of 0t. Corresponding to this repeated root, we have a part of CF as C1, C2 plus C3t into e to the power of t. This is CF. Now you convert t in terms of x using the known substitution. E to the power of t is x, t is log x. So complementary function contains 3 arbitrary constants c1, c2, c3 because the given differential equation is of third order. So complementary function is c1 plus c2 plus c3 into log x into x. Now pi is 1 divided by f of d. F of d is d cube minus 2d square plus d operated on e to the power of t. This is like e to the power of at type 1. We have to replace d by 1 because the coefficient of t is 1 here, but if we replace d by 1, denominator becomes 0, and hence we have to multiply t and differentiate the denominator. Multiply by t, t is the independent variable here. Differentiate the denominator, which is 3d square minus 4d plus 1 operated on e to the power of t. This is f dash of t. Again, type 1, we have to replace d by 1, coefficient of e to the power of coefficient of t here in the e to the power of t. E to the power of at, a is 1 in this case. If we replace d by 1, then even this f dash of d becomes 0. 3d square minus 4d plus 1 becomes 0. So the rule is t square into 1 by f double dash of d. This is derivative of denominator. Derivative of 3d square minus 4d plus 1 is 6d minus 4 operated on e to the power of t. Now you can replace d by 1 here. It is t square into 1 divided by 6 minus 4 e to the power of t. That is equals to t square e to the power of t divided by 2. Now convert t in terms of x. T is log x, e to the power of t is x. So we get pi as log x the whole square into x divided by 2. Therefore the complete solution is y equals to cf plus pi. Cf is c1 plus c2 plus c3 log x into x plus pi is log x the whole square into x divided by 2. This is Cauchy's differential equation. Now next topic, Legendre's differential equation. An equation of the form an into ax plus b whole to the power of n dny by dx to the power of n plus an minus 1 ax plus b whole to the power of n minus 1 into n minus 1 the derivative plus some constant an minus 2 into ax plus b whole to the power of n minus 2 into n minus 1 the derivative of y with respect to x, and so on. Ax plus b into dy by dx plus a naught into y equals to phi of x, where all ai's are constants and phi of x is a function of x or constant, is known as the Legendre's differential equation. So it follows some pattern similar to Cauchy's differential equation. This reduces to Cauchy's differential form when a is 1 and b is 0. In that case it becomes an into x to the power of n, nth derivative of y with respect to x. So procedure of solving Legendre's differential equation remains same as Cauchy's differential equation. So we need a suitable substitution. In Cauchy's it was x, here it is ax plus b. So the substitution is put ax plus b equals to t. Yes, in Cauchy's it was x. Put ax plus b equals to e to the power of t, then t becomes log of ax plus b. Now chain rule. X is a function, y is a function of x, x is a function of t. So dy by dx becomes dy by dt into dt by dx. I have written dy by dt as it is. Dt by dx is 1 by ax plus b into a. Derivative of t with respect to x. Log of derivative of log of ax plus b is 1 by ax plus b into integral differentiation of ax plus b is a. You cross multiply ax plus b, you will get ax plus b into dy by dx equals to a into dy by dt. So the term, the variable term in the equation ax plus b dy by dx got converted into a term with constant coefficients a into dy where d represents a derivative with respect to new variable t as before. This is about first order derivative. The same concept is used for second order derivatives. We can easily prove that ax plus b whole square into d square over dx square reduces to a square into d minus 1 into y, and ax plus b whole cube d cube y by dx cube becomes a cube into d minus 1 into d minus 2 into y. The only extra parts are a square and a cube in the RHS, which we get when you differentiate ax plus b. we get a there. There is the extra part. Now problem 1 on Legendre's differential equation. Solve 1 plus x the whole square into d square over by dx square plus 1 plus x into dy by dx plus y equals to 2 into sine of log of 1 plus x. You can see coefficient of d square over dx square is 1 plus x the whole square. The same thing here, 1 plus x into dy by dx, and coefficient of y is constant here. So this is Legendre's differential equation with a being 1, coefficient of x, a is 1 here and b is 1. This can be reduced to a differential equation with constant coefficients using the substitution ax plus b equals to e to the power of t, which is nothing but 1 plus x equals to e to the power of t. So t is log of 1 plus x and x is e to the power of t minus 1. With this, when you substitute all these things, of course, after changing this, as I mentioned earlier, the variable coefficient term 1 plus x into dy by dx becomes a into dy, a is 1 here, and 1 plus x whole square into d square over dx square becomes a square. This is a square term, which is 1 here, 1 square into d minus 1 into y, which is nothing but d into d minus 1 of y, where d is derivative with respect to new variable t. When you substitute all these things in the given differential equation, we get d into d minus 1 of y plus dy plus y equals to 2 sin t. Simplify this, we get d square plus 1 of y equals to 2 into sin t. Auxiliary equation is m square plus 1 equal to 0. You solve this, we get a pair of complex roots 0 plus r minus I. So the complementary function is e to the power of 0t, 0 is the real part, into c1 cos t plus c2 sin t. Now convert t in terms of x. Complementary function is c1 into cos of t is log of 1 plus x plus c2 into sine of log of 1 plus x. This is complementary function. Now pi. Pi is 1 divided by d square plus 1 operated on 2 sin t. 2 is constant, dig it out. 2 into 1 by d square plus 1 operated on sin t. This is of the form sine of ax plus b, and it is type 2. In type 2, we have to replace d square by minus of a the whole square, where a is this one, sine of ax plus b. In this case, a is 1, but if we replace d square by minus a square, denominator becomes 0, and hence you multiply by the independent variable, which is t here, and differentiate the denominator, which is 2d, operate it on sin d. So 2t by 2 becomes t. This 1 by d stands for integration. So 1 by d sin t is integration of sin t dt, which is nothing but minus t cos t. Integration of sin t is minus cos t. Now convert t in terms of x. So pi is minus log of 1 plus x plus cos of log of 1 plus x. The required solution is CF plus pi as given. Next, problem number 2. Solve 3x minus 2 whole square into d square over dx square minus 3 into 3x minus 2 dy by dx, that is equals to 9 times 3x minus 2 into sine of log of 3x minus 2. You can see coefficient of d square over dx square is like ax plus b with a as 3 and b as minus 2. And this is same thing, this is some a naught or a n, whatever it may be, 3 into 3x minus 2 dy by dx, and RHS are terms independent of y, which is 9 into 3x minus 2 into sine of log of 3x minus 2. So this is Legendre's differential equation with a equals to 3 and b equals to minus 2. This can be converted to a differential equation with constant coefficients using the substitution 3x minus 2 equals to e to the power of t. So that t becomes log of 3x minus 2 to base e, and from 1 we can write x as e to the power of t plus 2 divided by 3. So these are the corresponding transferred terms. 3x minus 2 into dy by dx gets transformed to 3 into dy, 3x minus 2 whole square d square over dx square gets transformed to a square, a is 3 here, a square into d minus 1 into y, which is 9 times d into d minus 1 into y. Substitute all these things in the given differential equation. It's 9d times d minus 1 of y minus 3 times 3 dy equals to 9 e to the power of t sine t. This is the RHS part, sine of log of something got converted to sine t into 9 e to the power of t. You simplify this, we get d square minus 2d of y equals to e to the power of t into sine t. This is an equation with constant coefficients. Its auxiliary equation is m square minus 2m equals to 0. Solve this to get roots as m equals to 0 and m equals to 2. The part of CF corresponding to m equals to 0 is C1 into e to the power of 0t. For m equals to 2, it is C2 e to the power of 2t. We can write e to the power of 2t as e to the power of t the whole square, and then you replace e to the power of t by 3x minus 2. So complementary function is C1 plus C2 into 3x minus 2 the whole square. Now pi. It's 1 over f of d into phi of d. F of d, the operator is d square minus 2d, where d represents derivative with respect to new variable t, operated on e to the power of t into sine t. This is like e to the power of ax into v of x. It's type 4. Take e to the power of t outside the operator after replacing d by d plus 1. So pi becomes e to the power of t into 1 by d plus 1 whole square minus 2 times d plus 1 operating on sine t. You expand it and simplify it to get e to the power of t into 1 by d square minus 1 sine t. Now this is type 2, sine of ax plus b. Rule is replace d square by minus of a square. A is 1 here, so you have to replace d square by minus 1. So when you replace d square by minus 1, we get pi as minus e to the power of t into sine t divided by 2. Now convert this in terms of x. T is log of 3x minus 2 sine of t, which is log of 3x minus 2, e to the power of log of f of x equals to f of x. Use that concept. You can write this e to the power of log of 3x minus 2 as 3x minus 2 into sine of log of 3x minus 2 divided by 2. Okay, so it is minus 2 here. 3x minus 2 into sine of 3x minus log of 3x plus 2. So answer is y equals to CF plus pi with a negative sign in the denominator. Done. Problem number 3. Solve x plus 1 whole square into d square y by dx square plus x plus 1 minus y equals to log of x plus 1 whole square plus x minus 1. You can see the coefficient of second order derivative is x plus 1 whole square plus x plus 1 minus y equals to log of x plus 1 whole square plus x minus 1. Okay. You can see there is x plus 1, y dash is missing here. If there is no y dash, you transfer it to right hand side because it's a term independent of y. This is x plus 1. If there is x plus 1 into y dash, then we can write it as 1 into dy. If there is no y dash here, transfer this term to RHS. So what I have done here, okay, I have used dy minus y term, so there is a y dash term there. I have not shifted this to RHS. There is a y dash term in the question. It's x plus 1 into y dash. Now, this is the RHS part. After simplification, you simplify it. D square minus d plus d minus 1 of y equals to 2t plus e to the power of t minus 2. You simplify this equation to get this form. D square minus 4d plus 2 of y equals to 3 into e to the power of t minus 15 divided by 4. Okay. This is not the CF. No, this is not the differential equation. Differential equation is this one. This is d square minus 1 of y equals to 2t plus e to the power of t minus 2. So auxiliary equation is not this, not with respect to this part. This is with respect to d square minus 1. Auxiliary equation is m square minus 1 equals to 0. So m equals to plus or minus 1 are roots of auxiliary equation. This is root corresponding to plus 1 and this is root corresponding to minus 1. CF corresponding to the root minus 1. You write this using law of indices and then you replace t by x plus 1. You will get CF in this manner. So this is not the part of this question. D square minus 4d plus y equals to 3 to the power of t minus 15 by 4. So you omit this line. Done. Now pi is 1 by d square minus 1, 2t plus e to the power of t minus 2. So there are three terms here. 2t, which is a polynomial. Next, e to the power of t, e to the power of ax plus b form. And then we have minus 2 here, which is a constant. So you separate it. 2 times 1 by d square minus 1 operated on t. 1 by d square minus 1 operated on e to the power of t. And minus 2 times 1 by d square minus 1. I can write this as 2 into e to the power of 0t. So first term is a polynomial type, so type 3, and next two terms are related to type 1, which is e to the power of at plus b form. You can write pi as 2 times pi1 plus pi2 minus 2 times pi3. Let me find all these things separately. pi1 is 1 by d square minus 1 operated on t. There are only two terms, so binomial expansion is easy in this case. You can write d square minus 1 as minus of 1 minus d square operated on t. Take this to numerator, we get 1 minus d square whole to the power of minus 1. You expand it using binomial expansion, which is 1 plus x square plus x to the power of 4. So 1 plus x, this is x term, this is x square term, and so on. As this is a polynomial of degree 1, second order derivative as well as fourth order derivative of t are 0. You are just left with this term 1 operated on t, which is t with a negative sign. So pi1 is minus t. Now let us find pi2. pi2 is 1 by d square minus 1 e to the power of t. This is type 1 form. We have to replace d by a. Here a is 1. If you replace d by a, denominator becomes 0. So the rule is you have to multiply by the independent variable and differentiate the denominator. Derivative of d square minus 1 is 2d. 1 by 2d into e to the power of t. Yes, of course, here there is no need to integrate like this. You can directly replace d by 1 to get the same result, t by 2 into e to the power of t. Or else 1 by d stands for integration, so integration of e to the power of t is e to the power of t again. Or else simply just replace d by 1 to get the same result. This is pi2. pi2 is 2 by 2 into e to the power of t. Next pi3, 1 by d square minus 1 operated on e to the power of 0t, which is a constant. Now as usual, replace d square by d by 0 to get pi3 equals to minus 1. Now the particular integral is 2 times pi1 plus pi2 minus 2 times pi3. Substitute all these things, simplify, and then convert this in terms of x using known substitution. T is log of x plus 1, e to the power of t is x plus 1. You get pi in this fashion. So required solution is y equals to complementary function plus ci. Now problem number 4. Solve 3x plus 2 whole square into d square over dx square plus 5 times 3x plus 2 into dy by dx minus 3y equals to x square into x plus 1. The coefficient of second order derivative is 3x plus 2 the whole square, which is like ax plus b whole square. In this case, a is 3 and b is plus 2. This equation reduces to equation with constant coefficients using the substitution 3x plus 2 equals to e to the power of t. So x is e to the power of t minus 2 divided by 3. You convert all terms with variable coefficients to constant coefficients using the known technique. 3x plus 2 into dy by dx equals to a into dy. A is 3. Next, 3x plus 2 whole square d square over dx square is a square into d minus 1 into y. A square is 9, where d is derivative with respect to new variable t. Substitute all these things in the given equation. LHS is 9 times d into d minus 1 into y plus 5 times, that is first order derivative, 3 dy minus 3y equals to now right hand side. This is x square term, which is e to the power of t minus 2 by 3 plus x term e to the power of t minus 2 by 3, and this is a constant present in it, 1. Multiply 9d, you get 9d square minus 9d plus 15d minus 3 here, operated on y gives, you expand this to get e to the power of 2t minus 4 e to the power of t plus 4 divided by 9 plus e to the power of t minus 2 by 3 as it is, 1 as it is. Okay, you take 3 common here and simplify to get this equation, 3d square plus 2d minus 1 of y equals to e to the power of 2t minus e to the power of t plus 7 divided by 27. This is a linear differential equation with constant coefficient with respect to new independent variable t. So auxiliary equation is 3m square plus 2m minus 1 equals to 0. Factorize it to get the roots as m equals to 1 by 3 and m equals to minus 1. Roots are real and distinct. So complementary function corresponding to the root 1 by 3 is c1 e to the power of 1 by 3 into t, and the part of cf corresponding to the root minus 1 is c2 e to the power of minus t. Now convert this in terms of x by using law of indices. You can write e to the power of 1 by 3t as e to the power of t whole to the power of 1 by 3 and e to the power of minus t as e to the power of t whole to the power of minus 1. Next, using this known substitution, you convert e to the power of t in terms of x, which is 3x plus 2. So the complementary function of the given differential equation is c1 into 3x plus 2 whole to the power of 1 by 3 plus c2 divided by 3x plus 2. Let me find pi now. Pi is 1 over f of d operated on phi of t, e to power of 2t minus e to power of t plus 7. So apply on all the three terms, e to power of 2t by 27, 1 by 3d square plus 2d minus 1 operated on e to power of t, plus you can write the constant 7 as 7 into e to the power of 0t. Next, this is type 1, straightforward. You can just replace d by 2 here to get the solution. So when you replace d by 2, you will get Pi as 1 by 27 e to power of 2t by 15 minus e to power of t by 4 minus 7. And when you convert t in terms of x, you get the Pi in the form given. So Pi is 1 by 27, 3x plus 2 whole square by 15 minus 3x plus 2 by 4 minus 7. So the required solution is y equals to Cf plus Pi. So with this, I'll finish today's session. In the next class, I'll solve some more problems on Legendre's differential equations involving some boundary conditions. Thank you.